Hello, I am Simona, and I'm very grateful to the organizer for inviting me to present our work with Mikko in this special format, and really looking forward to meet you in the discussion session. So let me start by breaking down a bit my title, General Scalar-Induced Gravitational Wave Source for Reheating Dynamics. What we really want to do is to derive the source term of gravitational waves produced by primordial scalar perturbations in the early universe. And in particular, we are interested in the production during the reheating epoch, meaning the transition from inflation to radiation domination, remaining as general possible, so non-model specific. And we want to work in an arbitrary gauge in order to be able to use gauge invariance as a cross-check of our results. And why do we want to do that? Well, first of all, the spectrum of scalar perturbations is constrained at small frequencies by the observation of the cosmic microwave background anisotropies and the correlation of the large-scale structure. But this is a small frequency window, and if we go at larger momenta, then deviations from the scale invariant spectrum are possible, and even possible are some peaked features. And what is exciting about the peaked features is that they might facilitate the formation of exotic objects, like, for example, primordial black holes or early galaxies that are linked to new observables like the little red dots and so on. But what is really exciting for us is that peak features in the scalar power spectrum might also boost the production of gravitational waves in the early universe. And gravitational waves might represent a unique probe of the reheating epoch. And reheating epoch, again, is in our definition this transition period that connects a vacuum-dominated inflating universe with the thermal state at equilibrium that should dominate at least at the time of Big Bang nucleosynthesis. And this is quite a difficult period to study and to constrain, because the scalar modes that are observable at the CMB, they are outside the horizon during this period, during the reheating. But other modes, in particular those with larger frequencies, they might also re-enter during reheating. So now to give a picture to what I'm trying to express, let us put the scale of physical momenta on the y-axis and time on the x-axis. Now the expansion of the universe, the Hubble rate, determines the scale at which a momentum feels local dynamics or freezes out, only feels the expansion of the universe. And during inflation, this scale is constant in time, and then it transitions to the power law that characterizes radiation domination. So whenever a mode is characterized by a physical momentum larger than the Hubble rate, then we can say that it feels local dynamics. It is inside the Hubble horizon. And an interesting trajectory of a scalar mode for us is the one sketched by the pinky band. So during inflation, we have exponential decrease of the physical momentum, and if the momentum initially is large enough, then the freeze out happens just at the end of inflation, and the mode re-enters short afterwards when we are still in this transition period, in reheating. And what is even more interesting is that while we are in this transition period, what could happen is that while during inflation, the dominant equation of state has negative pressure, and during radiation domination, the pressure is positive. In this transition period, we might have a moment where the dominant component of the energy density is pressureless. So we are in an early matter domination. And this early matter domination has been shown to be able to boost the production of gravitational waves at second order from scalar perturbations. There are several mechanisms for that. They are all very interesting, very nice, and there is plenty of literature about. So the mechanism right now is not really the topic of my talk. What we rather want to do is to derive the correct equation to deal with the gravitational wave dynamics sourced by these scalar modes at second order precisely in this period. This because historically the scalar-induced gravitational wave equation has been derived for applications most commonly already during radiation domination and also during inflation. So we want to focus really on this particle dynamics where we have many degrees of freedom with a non-trivial interplay. And our method is not very creative. What we do is that we expand metric and energy momentum tensor in background plus perturbations, and we evaluate Einstein equations staying at linear order in tensor perturbations and going to second order in scalar perturbations. Once we have done that, we project to traceless and transfer special components, and we shape our result in such a way that on the left-hand side, we have a D'Alembert operator acting on geometric tensor perturbations, and on the right-hand side, we have a source term, an effective source term. And then once we have such a differential equation, the solution can be found with the green function method, but again, this is another story, and here we just focus on the derivation of the equation. So let's go. First, on the left-hand side, we have the metric, and we work in conformal coordinates, where tau is our conformal time, A is the scale factor describing the expansion of the universe, and the metric is given by the homogeneous and isotropic background, which is on diagonal, plus scalar perturbations and tensor perturbations. And since we restrict to traceless and transverse tensor perturbation, we only have 2 degrees of freedom for them, and we have 4 scalar degrees of freedom. And because we have the freedom given by coordinate transformations in general relativity, then only 2 linear combination of the 4 scale variables are linearly independent, so are physical. This means that we can define 2 gauge invariant variables to work with. And for example, we can define the famous Bardeen potentials, phi and psi, and substitute 2 of our previous scalar variables with phi and psi. But even if we do so, say we substitute h0 and y, then we retain h and theta in order to keep track of the ambiguity of gauge transformations, and in order to be able to reconstruct any gauge from our results. So now we take these variables, and we have the metric, so we can compute Christoffel symbols, Ricci tensor, Ricci scalar, and we are left with an Einstein tensor that contains many terms. So we said we are linear in the tensor perturbations, but then we have all the terms quadratic in scalar perturbations. Some of them are quadratic in the gauge invariant variables, so all is fine. But others involve a single or even double appearance of the ambiguous, unconstrained variables. But okay, let's keep calm and go to the right-hand side. On the right-hand side, we have the energy momentum tensor. And since we want to describe the transition from inflation to radiation domination, we include the inflationary sector, so we say inflaton, and also fluids, which are described by their energy densities, pressure, and flow velocities. We also take into account anisotropic stresses, which, for example, could describe the contribution of the viscous corrections to the fluid motion. And then we expand again in background plus perturbations. But in doing so, since we said we go to second order in scalar perturbations, we also keep in mind that we are working with fluids. So implicitly, we are in the hydrodynamic approximation. And therefore, we should consider the anisotropic stress contribution to be a higher order term, so to be second order term. And moreover, we keep in mind that we also have metric perturbations showing up on this side of the equation. Then analogy with working with Bardeen potentials, also for the energy momentum tensor, we can define two gauge invariant variables, and we choose curvature perturbations. And what is nice about the choice of these variables is that by evaluating Einstein equation at first order, we can derive a closed set of stochastic equations for those curvature perturbations and the Bardeen potentials, which can be solved separately. And from the solution, we see that independently on the choice of the variables, and I show here 3 cases taken from our previous work with Alexa, then independently of the choice of the parameters, in the period where the mode are frozen out of the Hubble horizon, so the beginning of each plot, the curvature perturbations freeze to the very same value. But then once they re-enter the Hubble horizon, their dynamics decouples and they start oscillating independently from each other. And like in the plot on the left, this moment where they re-enter the horizon is later, and going to the right, it's earlier and earlier. So we can see how complicated is the dynamics we want to capture after horizon re-enter. So let's evaluate the right-hand side of the energy momentum tensor. We really have many terms here. Again, we have a linear term in the metric tensor perturbations, which is nice because it cancels against the left-hand side. Then we have contribution from the anisotropic stress. We have those terms that are quadratic in gauge invariant variables. Fine again. But then we have many terms that involve a single or double appearance of these unconstrained scalar variables. So now the last step to do is to equate the left and the right-hand side of the Einstein equations and see how these terms combine. And this requires many manipulations and cosmetic work until we get to something that can be written in a compact way. And of course, one can go on forever, but at some point we decided we are fine with the result, which is this one. So on the left-hand side, we have, as wished, the D'Alembert operator acting on the tensor perturbations of the metric. And on the right-hand side, most importantly, first of all, we notice that whenever we have a single or double appearance of those unconstrained variable, then we can write these terms in the form that we have a D'Alembert operator, again, acting on terms. So this means that these terms affect the gravitational wave amplitude only by its value today. They are non-propagating, and we can take all of this on the left-hand side and combine with theta ij. So now the equation looks already a bit better. We are still left with two terms, one involving h and one involving theta, that also contain the linear combination of psi minus phi. But from the first order Einstein equations, we know that psi minus phi is related to the anisotropic stress. And we have said that the anisotropic stress for us is a higher order term, second order. So if we are in the hydrodynamic approximation, then these ambiguous terms also are negligible. And we are left with this result where indeed we can extract physical information, because on the right-hand side we have an effective source term which is able to capture the reheating dynamics. And on the left-hand side we have this linear combination that can be shown to be gauge invariant at second order. So now what is left is to solve these equations numerically, and we are very excited. But before I conclude, let me also flash a little advertisement of our upcoming book, where all the results, also that I have presented today, are presented step by step. So if you are interested in reheating dynamics, please stay tuned. And with that, that's all. I thank you very much for your attention and see you soon.